I did summarize these two sets of rules. I think we've already seen the aromatic, but you haven't seen the anti-aromatic rules. So they're effectively the same thing. It just comes down to a differing number of pi electrons. Okay? So we're going to end up spending a good portion of today pretty much looking at more examples of these, and then hopefully getting into reactivity of the benzene or the benzylic position. And then we'll be done with chapter 18 slides, and we'll move into chapter 19, which is going to be all about ultimately EAS reactions. We'll see some other reactions in there too. Okay, so one of the last examples we ended with was looking at the one that I can't refer to, looking at its orbital arrangement and whether or not it classifies as aromatic or not. Okay? And it turns out that if we look at the molecular orbital picture, that we would classify it as anti-aromatic. And the reason it's anti-aromatic is because, so we could go back to the rules, okay, or we could look at the molecular orbital diagram and see that we have unpaired electrons. Those unpaired electrons are a destabilizing factor in the overall structure, and that puts us into the anti-aromatic category. Okay? Whereas the aromatic category has everything paired, and that pairing contributes to stability of the overall compound and makes it more stable. Okay? So if we look at the orbital diagram for this, we can see that we would get an anti-aromatic alignment because we don't have the proper pi electrons for it. And it turns out in the case of this structure that to avoid that anti-aromaticity, what it will do is pucker. So the structure bends a little bit. That kicks the pi orbitals out of alignment with each other. So now you no longer have that conjugated system. And because of that, you also lose the anti-aromatic destabilizing factor. Okay, so it's kind of a structural perk. Okay, so it just kind of tweaks away from that. So if we took a look at this compound, would we expect this compound to be aromatic or anti-aromatic? Okay, how are you figuring it out? What are you doing? Okay, so we go through and look at our pi bonds. 1, 2, 3, 4, 5, 6, 7. I'm going to be a bit obnoxious. Last one I'm going to color in a different color. So 8 pi electrons, right? 8 pi electrons means even number, and we would think anti-aromatic. Turns out it's not anti-aromatic. Okay. So one of the contributing factors when we're looking at aromaticity is ultimately resonance. So what we could try and go through and do is pick any of these pi electrons and try and draw resonance structures. And if we can draw resonance structures where they circle back on themselves, we end up generating just an alternating arrangement of those double bonds, like we did with benzene. It's one of our appearances for an aromatic structure. And what the rules that they generated happen to follow those kind of patterns. Doesn't mean they always work. If we say take that orange pi bond and try to do resonance and moved it outwards, okay, we could push our pi electrons around. Okay, and you'll notice that we end up eliminating one pi bond. Okay, it doesn't show up in the resonance. If you go through and alternate different possible arrangements of how you're pushing those pi bonds, you'll find that you will always not include one pi bond. Okay, what does that mean? Instead of there being 8 pi electrons involved in the pi system, it turns out there are 7 pairs of pi electrons. One of those pi bonds is completely ignored. Okay? For, I guess, symmetry's sake, if you take a look at the textbook slide notes, it actually says that you ignore the middle double bond. I don't think it has to be the middle one. That just happens to be the easiest one to isolate on its own. Okay? So it's kind of a tricky thing to watch out for. It's not always, oh, there's a pi bond, that means it's part of the pi system. Okay? You have to evaluate and make sure that pi bond is indeed part of the pi system. In this case, when we go through and move the electrons around, we'll find that one pi bond is not part of the pi system and should not be counted in our pi electrons. Okay? So you've got to be a little bit careful with that. I ended real quickly and said there was a simple way that you could look at the molecular orbitals, and that's looking at what they're referring to as frost circles. So if you draw a circle and then inscribe the shape of your pi system within that circle with the point aimed down, why would we put the point downwards? These are all supposed to represent what? Yeah, our molecular orbitals. The lowest energy orbital is going to be when all of the p orbitals align with each other. Is it possible to get all of our p orbitals aligned with each other in two different ways, or more than one way? No. Okay, so we'll always aim our polygon with the point downwards. It's always going to be the way it works. You can then go through and at each of those points, you can then put in a molecular orbital. In theory, you can draw your baseline energy level through the dead center of that circle. If you're drawing a circle, you probably don't know where the dead center of that circle is. So we kind of have to take a little bit of, take it a little bit for granted as far as finding exactly where those orbital energies are. And then we can erase all of our extra sketch information to end up with our molecular orbitals. Okay? Anything above that center line is an anti-bonding orbital. Anything below that center line is a bonding orbital. Okay? And then we could then put in our pi electrons and figure out if we've got paired or unpaired. Okay? So it works as a very good approximation as far as putting these things together. It's not strictly necessary because you could go through and have those rules memorized for what makes it aromatic or anti-aromatic. Okay? So the intent is that this could allow you to derive those rules. Okay? So we can come back to the rules again. We're looking at those p orbitals. We need the p orbitals to overlap to allow for that increased resonance. When it's aromatic, we have a very particular set of pi electrons, and that's where we're getting, I think I numbered them out before, as far as numbers of electrons that we have. It was 2, 6, 10, 14. Okay, so it's almost easier to just memorize the number of electrons in the pi system as opposed to the formula. Because what are the odds that you're going to start pushing beyond 14 pi electrons? Okay, you're starting to get larger and larger structures. The bigger the structure, more difficult for me to draw, less likely I'll answer or ask the question. Okay? And think about it this way as well. The ACS test is going through the same process, going through the same thought process as I would as far as building these structures. Okay? When it's anti-aromatic, your formula for your pi electrons drops to just 4n pi electrons. Okay? What did the n stand for again? Yeah, it's just any whole number integer. Okay? 0 up to an infinite amount in theory. Okay? So other things that we want to take into consideration are the structural effects. So we could look at a couple other compounds and try and decide if they're aromatic or not. Okay? So in each of these cases, you'll notice that our naming system here is looking at the pi electrons, so 6, 10, 14. All of those are part of our pairs of electrons, right? We said 2, 6, 10, 14. So all of those, according to Huckel's rule, would be expected to be aromatic. We've got those p orbitals, and at least the way they're drawn, it certainly looks like we would have aromatic compounds. Turns out the middle one, 10-annuline, is not aromatic. Why? Has to do with its structure. Turns out it's not planar. Why is it not planar? It's got pi bonds, alternating pi bonds just like every other. What's the issue between those two hydrogens? Yeah, they're going to repel. You get a steric repulsion that causes the structure to kind of pucker out of alignment. If that breaks it out of the planarity, you don't get the p orbitals all overlapping. You don't have that overall effect. Okay? So these are kind of pseudo-neat structural effects. How much you would be expected to predict or see these is an entirely different question. I don't think I would ever ask anything along these lines, and I doubt the ACS test would either. Okay? But what I want you to do is be aware of these structural effects. Primarily, as it concerns to something about reactivity. Okay, so we've looked at through just carbon pi systems. That's been it. Carbons and hydrogens, that's all we've evaluated so far. Does it have to be only carbons and hydrogens? Turns out not. All we're counting are the pi electrons. However those pi electrons got there is completely irrelevant as long as they're in the pi system. Okay? So our rules, again, for it to be aromatic, we have to have that fully conjugated ring, so overlapping p orbitals. We're going to make a slight tweak to that. I like to put p orbitals in quotes. Okay. And we'll get into an example of that in a second. And then it's going to have to meet Huckel's rule. We have to have that odd number of electron pairs. Okay, so it has to match our numbers of electrons, again, 2, 6, 10, 14, and what, 18, right? Etc. So we take a look at the first structure, aromatic or not, or anti-aromatic. Should be aromatic. Why? All sorts of silly answers on that.
Meets the rule.
Meets all our rules.
Benzene.
Okay. Another answer might have been it's benzene. Okay. Benzene is our classic case. How about the next one? Okay. We do have the conjugated pi, p orbitals. So that rule is satisfied. If we move to the next rule, okay, we have to have that 2, 6, 10, 14. How many electrons do we have? We have only 4 pi electrons, which means anti-aromatic. So I'll just stick with AA. Next one. It's a hint, I am color coding.
Non-aromatic.
Okay, it's going to be non-aromatic. Why is it not aromatic?
It's not fully, doesn't have all the overlapping p orbitals.
Because of why? You're right.
Doesn't have all the
Where is
p
it?
orbitals overlapping at the top, the points.
What's the hybridization of that carbon?
SP3.
sp3. If it's sp3, do we have any leftover p orbitals? Nope. No p orbitals, no resonance. Okay. So our resonance would die at that point. Rule number 1 fails. We're looking at non-aromatic. Okay. How about the next one? Okay, since we started with it, we might as well check. Okay, what's the hybridization of that carbon? sp2, do we have that overlapping p orbital? Yeah, we do have the potential for that p orbital hanging out there. Okay, how many pi electrons are in this one?
4, but the lone pair.
We have 4 pi electrons. What lone pair are you talking about?
Oh, no, I'm sorry.
Okay. That is an sp2 carbon with a positive charge, meaning it lacks electrons, which would suggest that we are looking at an anti-aromatic structure. Okay. Next one. Non-aromatic because it's not a ring. Okay. It has to be cyclic. They have to fold back on themselves. Okay. Next one. It's a trickier one. And now we're actually making it different, getting back to the main question, which does it have to be a carbon pi system? So, not to give away any answers or anything, but how many pi electrons do we have? Where are they? Our pi bonds, right? Okay. That would suggest only 4 pi electrons, which would put us in that anti-aromatic category. Okay, but I used red, so very clearly, it's got to be aromatic. So to become aromatic, what does it need?
2 more electrons.
It needs 2 more electrons, okay, in a pi system. Do we have 2 electrons in a pi system? Okay, you're shaking your head yes. What's the hybridization of that atom?
sp2.
Is that really what it looks like right now? How many electron groups are there? That looks like sp3. Okay, so here's where I like to put the quotes on the p orbitals. When we look at our overall structure there, at least the way it's currently drawn, the hybridization on that oxygen is sp3. No p orbital electrons. However, could we draw resonance? I can take those pi electrons and move them into a bond and move the other pi electrons out onto an atom. In that case, and sorry for the colors in the lower right-hand corner, just going to draw over the top, make it look like a little gorilla face. Charge on our oxygen now becomes positive. What's the hybridization of that atom? Now it's sp2. By doing resonance, we can cause a pair of electrons on that oxygen to become part of the pi system, which means when we go through and count the pi electrons, how many pi electrons do we have? We've got 6 pi, which makes that structure aromatic. Kind of tricky. So we can bring in pi electrons. Remember, we did the same kind of thought process before. Our cycloocta, not nameable one, puckered out of being planar. Why? Because it didn't want to be anti-aromatic. What's happening in this case? Okay, we're looking at a cyclopentane, effectively, that is naturally going to have that envelope shape, so not planar. But if that oxygen drops down to within the plane of the rest of the atoms, what happens? Now it's aromatic. If it's aromatic, it drops in energy. So it's going to sacrifice a little bit of that angle strain to go through and actually make it aromatic, okay, and make that conjugated pi system. So we can get structures bending and transitioning to get out of the anti-aromatic conformation, and we can also get them bend and change to get into an aromatic conformation. Okay? What happens with the very last one? Nice and crowded in there. What do you think? Aromatic, anti-aromatic? I'll be a jerk here. Come up with a different color. So I see pi bonds. Okay, so we got at least 4 pi electrons. If it stayed at 4, we'd be what? Anti-aromatic. If we can somehow get 2 more electrons into that pi system, we can become 2 more electrons in, and we become aromatic. Okay, do we have some more electrons floating around on the outside of that structure? We got 2 nitrogens, 2 sets of lone pairs that could potentially be involved in this. But if I bring in both lone pairs, what happens? Anti-aromatic. So I can only bring in 1. Okay, well, are those lone pairs the same? No, only 1 pair of electrons in that case can actually physically contribute to the pi system. The other one is physically impossible for it to get into. Which nitrogen has lone pairs that can actually contribute? Top or bottom? Top is a good answer. Okay. We've got our 6 pi electrons. This becomes aromatic. Okay. I can't remember if I've got it shown up there in another spot or not. When can we bring in a lone pair? That lone pair has to show up on a very particular atom. Okay. It has to show up on an sp3 atom. Why does it have to be sp3? And again, because I said I'm not sure I've got it drawn, I'm going to take a look at it here. Look at our pi system, make that a nitrogen. The one that we currently had, that we said could count, this is our sp3. Here's our pi system as our wedge and dash. If we looked at the other nitrogen, this is going to look pretty ugly, but here's the double bond. Our nitrogen, where's the lone pair? Now out here. Okay. What's the bond angle between our pi system and the lone pair in the sp3 system. 109.5, we can actually rotate that sp3 orbital up just a little bit to make it part of that system. Okay, that's our p orbital, is that up and down action. If we go in and take a look at the other one, this one's a little bit trickier to see. Our pi system is in that same up and down axis. Where's our lone pair? Straight out to the side. The geometry of that nitrogen is trigonal planar. Why is that important? To get that p orbital to overlap with the pi system, we have to do a pretty massive rotation to get it up into there. Okay, and at the same time, what happens if we rotate that p orbital up? The other lobe of our p orbital would rotate out and away. We don't get that contribution. Okay, so when we're looking at resonance through pi systems, the p orbitals have to be overlapping, okay, or close to overlapping, which is what's nice with our sp3 atoms. That sp3 atom can rotate into that structure and account for that bond angle change. It's a fairly subtle difference. In other cases, when we're looking at sp2 or even sp atoms, we can't get that rotation to get that p orbital, or sorry, that hybrid sp2 or sp orbital to get the electrons up into the pi system. Which means when we're going to look for overlapping p orbitals, okay, we can look just for p orbitals. Well, I won't write that one because that one's fairly obvious there. It's already stated. Or we can look for resonance, what I'll call resonance p orbitals. Because if we went through and drew a resonance structure, we can show that the hybridization of that, or in the case of the oxygen, changes. Or what we can do in general is just say, if you have an sp3 atom, you can count the lone pair. And you can only count one lone pair. What do I mean by that? When we did the oxygen, how many of the lone pairs did we count to our pi system? Only one of those pairs. What happened to the other pair? That shifts into the plane, away from the structure, just like our nitrogen here. Okay? So when you're trying to count for your pi electrons, realize they don't have to be in pi orbitals directly to begin with. They can be hidden in sp3 atoms. Okay, so kind of watch out for that. Another thing that we could go through and do, remember this compound we stated was not aromatic. We didn't have the option. Okay, not aromatic, because we didn't have that p orbital. Turns out that that compound's acidity, even though we're looking at arguably an alkane at that position, okay, at that carbon, the acidity of that position becomes astronomically higher, much, much, much more acidic, okay, than if we looked at a standard alkane. Well, if that's the case, there has to be a reason why. Why would it become so much more acidic than ethane? Well, what we can do is take a look at our conjugate base. When we draw the conjugate base of our cyclopentadiene, put our lone pair on there, like our upside down gorilla. Take a look at our ethane, its conjugate base. Okay, and if we rank just the argument of the negatives themselves, okay, we might say ethane is more stable because the negative is on primary versus secondary. Okay, so when we're looking at anions, we would typically predict anions being more stable on lower substituted positions. Okay, but it turns out it's the opposite. We get more stability, okay, in the case of our cyclopentadiene. Why? Well, look at the product. We can draw resonance within the conjugate base, okay, but even if we added an extra double bond with our ethane, we'd still get a stronger acid out of our cyclopentadiene. Okay, so not only do we have resonance, but what else? It's also aromatic. Okay, so aromaticity is this really important, has a huge impact on the overall chemistry. It's not just determining, hey, we have an aromatic versus non-aromatic compound. It's, hey, if I can make it aromatic, that's really good. It's going to try and do that as quickly as it can. Almost like you would do for a rearrangement. Right? If we generate a secondary carbocation, what happens? Structure rearranges to try and make a more stable carbocation. Right? We're seeing something similar in this case. That structure becomes a lot more acidic because if it can get rid of that hydrogen, we now generate that aromatic and stable species. Okay? The other thing we do is look at all the resonance. Okay? I'll leave you guys to figure that out and see that that's indeed what's going on with it. Okay, so we could go back to all these rules. I was going to break it up, but I decided not to. So we could continue through the rest of those like we already did. And now we could look at the heteroatom contribution. So in this case, what we're doing is effectively looking at that last example. In the case where our nitrogen is sp2 hybridized, which is our pyridine example, versus our pyrrole, where we're looking at that sp3. And what we're trying to do is to predict something about the stability, okay? Or in this case, the reactivity. Which of these would we expect to be more basic? For it to be basic, what does it need to do? All bases do this. They need to donate electrons. Okay, if we're looking at a Bronsted-Lowry base, it's donating the electrons to hydrogen. If we're looking at a Lewis base, it's donating the electrons to anything other than hydrogen. All right, so where's the most basic atom in both of these cases? We're looking at our nitrogens. For it to be basic, those electrons need to leave the structure. If we can draw them going into the structure, that's doing the absolute opposite of what our base needs to do. So when we evaluate the lone pairs in each cases, can we draw resonance for each of those? Right, one of the standard options that people like to do is say, well, I can draw pi electrons doing this, right? Okay, it sure looks like that would be physically possible. Where's the lone pair versus the pi system that it has to pass into? Just drew it. They're perpendicular orbitals. Okay, we can't physically get those electrons into the pi system. If we take a look at the pyrrole, what happens with that? We're now shifting from the sp3 into the pi system. That sp3 is a lot closer to a p-type orbital than an sp2. This is where they drew it out a little bit nicer than I attempted to do. Okay, so when we take a look at our pyridine, the electrons, or the pi electrons, are in a perpendicular orbital to your pi system, okay, that lone pair. To be able to get those electrons into the pi system, we would actually have to destroy the pi system and reform it, okay, which kind of defeats the purpose of trying to do it to begin with. Okay. If we take a look at our pyrrole, what happens? All we've got to do is rotate very, very gently from our 109 up into that 90-degree angle to get our overlapping pi system. Right? What does that mean as far as the reactivity? Well, which is predicted to be the stronger base? Pyrrole or pyridine? Where do the electrons in the pyrrole go? Into the pi system. For it to act as a base, where do the electrons need to go? Out of the pi system, okay, towards a hydrogen if we wanted. Which means which one's the stronger base? Pyridine. Okay, so we can use aromaticity to predict some forms of chemistry. That's kind of the idea behind a lot of this. Okay, questions about that? Okay. So that's exactly what we're going through and trying to show here. They're showing it in kind of a different sit format. What are they showing it based on? They're showing it based on acidity. So they're looking at the product acids and saying which one's more stable or not stable. Okay, and how does that affect your overall system? Okay, so it's just a flip of what we just discussed. Another thing you could do is look at the electron density in each compound. So if you looked at density maps, you see in the case of pyridine, we have a large concentration of electron density outside that structure. That's why it's red on the edge. When we go to pyrrole, you'll notice that we do have a little bit of shifting of the electron density towards the edge, but for the most part, it's centralized. Okay? It does shift a little bit into the structure. And that's supposed to represent that your pi electrons are now shared through the middle of the structure. If they're in the middle of the structure, not very easy for them to get out and react with the hydrogen atom. Okay? Questions? Okay. Compounds other than benzene. If you were asked to try and show these to be aromatic using heats of hydrogenation, okay, what would we look for? So first off, are they aromatic? Yeah, we got 10 electrons in the first one. Naphthalene gives us 10 pi electrons. Anthracene gives us 14, and phenanthrene gives us 14 pi electrons. We do have overlapping p orbitals. We would expect these to all be aromatic. Okay, so that's based off of the Huckel rules. So we could go and just say, oh, they match the rules. We could also go try and show it using molecular orbital theory, using your frost circles. Okay, one more method. Okay, this is an easier way to ask it using multiple choice. Heats of hydrogenation. What would you predict in those cases? How would these be proven to be, or most likely seen to be aromatic if we used a heat of hydrogenation?
Aromatic compounds would have lower heats of hydrogenation.
So we always got to draw it out for me. We'd start with fully saturated, effectively at our bottom. Okay, why would the saturated be our lowest energy? What does saturated mean?
Full of hydrogens, no double bonds.
Full of hydrogens, no pi bonds. Why is saturated lower in energy than our pi bonds? Where are the electrons in our saturated structure? Immediately between atoms. And our unsaturated, with our pi bonds, where do we have some electrons? Above and below our atoms. So they're a little bit further extended away from the structure. Those electrons become a little bit more reactive. Okay. So we could go through and see that these are indeed aromatic because we could predict their energies based on how many double bonds we put into it. So in this first case, we got 5 double bonds. Well, we could say 5 double bonds. Each double bond is worth X amount of energy. That should put it up 5 times. So there's our 5. I'm just going to call it pi for the lack of creativity. And then we go through and we hydrogenate it. What's going to happen? When we hydrogenate, is that an exothermic or endothermic reaction?
Exothermic, give off energy.
Exothermic. We're adding hydrogen to the structure. We are going from our pi system to our saturated system. We just said our pi system was higher in energy, which means that energy has to go somewhere when we put in our hydrogens. That's going to be released as our thermal energy exothermic reaction. What would we expect to happen to the heat of hydrogenation if we had an aromatic compound? Should it be higher or lower? What does aromaticity do to the energy of a pi bond?
Lowers it.
Lowers it, which means the energy for our aromatic compound should be lower relative to our pi system. if we now look at our heat of hydrogenation, what happened to our heat of hydrogenation if it was aromatic? Bigger or smaller? Which arrow? Smaller arrow, which means less exothermic. Okay? There's less of a difference between your starting material energy and your final material, or your product. Kind of make sense? So that's what's going on with the heat of hydrogenation. Like I said, that is a question that is very, very popular on a lot of standardized tests. So watch out for heats of hydrogenation. If asked, I will do exactly what I just did right here. Draw out the energy diagram real quickly, predict where their energy should be, and then start looking at numbers. Okay? Takes time, but at least you get it right. Or at least I get it right. Other things we could go through and do is go back to our rules, which we already just talked about. So we could try and verify that they do indeed match those numbers. Okay. So there are all of our rules. We've got aromatic on there, anti-aromatic, and I added non-aromatic. Okay. Primarily when we're looking at non-aromatic, we're invalidating rule number 1. Okay, rule number 1 doesn't work. We don't have the overlapping p orbitals. It can be put in there as a kind of trick question. For instance, the quiz that you're about to take has a couple structures on it that I would argue are trick questions. Okay? Just because what happens? The structure decides to change its geometry. Well, if it changes its geometry, it can prevent itself from becoming anti. Okay, so if you think it's anti-aromatic, not a bad idea to specify anti-aromatic. Okay, if you can then look at it and say, I bet you that structure can tweak its geometry, go through and say that. Geometry changes, non-aromatic. That's why I would say it's a trick question. Whether you are able to see that it can tweak its geometry becomes the next question. Okay, and we looked at a couple examples. What was it, 10-annuline. You could look at steric hindrance butting up against itself. Okay? Those are not the easiest things to see, so as far as I sure hope the ACS exam and your test goes, you won't be expected to pick up the difference between those as far as trick questions go. Okay? So I'll try and add information to the question, like assume structure is planar, or assume it cannot move away from that standard geometry, something along those lines. Okay? Well, like I said, this quiz doesn't quite have that extra information, so it'll be a little bit trickier. If you got questions, raise your hand. Feel free to talk to the people around you. Just see what you can come up with. Where is it? There it is.